Alright, so let's get started. So draw sheet 2. The first question here, predict the major products for the following reactions and outline the corresponding detailed mechanism. If you look at what you've been given, like for the first one, you always need to identify the nucleophile and the electrophile. So if you look in this reaction, let me start with the first one. I'll write it again. Okay, so attached to oxygen there, we have got a sulfur, we have got oxygen. Okay, like that. Look at the compound that we have. We have got this one. So you need to identify. I had mentioned to say that when you see group 1 elements on bonded to some compound, those really don't affect the reaction. So here you actually have potassium positive and also amine like that. So this is going to be the nucleophile because it's negatively charged. Dimethyl sulfate, this is basically the solution in which the reaction is happening. So you need to identify the electrophile. The electrophile is the atom in the other compound that is positively charged. So if you see, this is oxygen. Since this is oxygen here, we know that oxygen is negatively charged. It's more electronegative. So expect that this sulfur should have a partial positive charge. Even this carbon here attached to the oxygen should have a partial positive charge. But then you go for the carbon because it's the one which is more electrophilic. So we are going to be able to attack this carbon. Okay. So the reaction is going to go like that, attacking this carbon, and then this is going to leave. Now when you look at this carbon is bonded to how many things? It's bonded to three different things, isn't it? In other words, it's only bonded to two things. If you look at the leaving group, it's bonded to another carbon here, another carbon here. So this is a secondary carbon, so it can undergo SN2 reactions. And so the next thing what we are going to be able to see is our product here. You can see that at the position where this big group was, that's where the NH2 is coming to attach. So this group can actually leave because it's a good leaving group. We'll discuss this in the next topic when we talk about alcohols. You hear things like tosylates, methylates. Those are good leaving groups. That's why this group here can get to leave. So this one is going to be a byproduct. It's not a major product. It's a byproduct. Like as O. Yes. Okay, so what you want to do is it should be in the opposite direction because when you're attacking, you're actually attacking from the back direction. So that is why you want to change. Initially where was the bond? It was equatorial. Now you can see it has gone axial, right? Yes. So that is because in SN2 reaction there is a reverse of configuration. So this is going to be the product. Make sense? Okay. So for the next one, we are using, I don't know how we can read this one. So also you can see that we have got sodium there. So this is going to be the nucleophile. Sodium is not affecting the reaction. You have got nitrogen. Nitrogen alone is negatively charged because it has got lone pairs. That's why we bond it to sodium so that that charge is not seen. So also here in the compound, you need to identify which one is the leaving group. Otherwise, if you don't identify the leaving group, you'll not be able to answer. So which one do you think is going to be the leaving group here? So halogens are the leaving groups. So what will happen is that for this reaction also, this guy is going to go and attack. But then look at this carbon here. How many things is it a primary, secondary, or tertiary carbon? So look at how many other things are bond. Yes, please. Okay. So this carbon is apart from the bromine itself, is bonded to other things. Yes, Richard. It's showing Richard. I hope it's a name. You can go on, please. Okay, so this is tertiary because the leaving group you can see the carbon is bonded to three other things except the leaving group. Now, when you have got tertiary substrates, the reaction is more likely to undergo the one reactions, either SN1 or SN2. Okay, mostly that's how the reaction is mostly going to undergo. But then another thing that you want to look at apart from that is you want to also look at the what? The nuclear of if is strong or weak. Now, we don't say this is necessarily tertiary because this thing they put here as D. Say that D is representing a hydrogen, then that is going to be secondary. If it is representing a carbon compound, that is going to be tertiary. So this one can as well go by SN2 reaction because this guy here is not a weak nucleophile. So this is going to go and attack and the leaving group is going to be able to leave. One thing that you should be able to identify is the configuration of your compound. If you can see this, let's say this is our group 1, this is going to be 2, this is going to be 3. You can see this one, it will be going like this. The configuration here is R. So you want to make sure that the product that you get, the configuration should be reversed. Otherwise, you are not correct. So for the configuration, because the leaving group was in front, you want the group that is coming in to be at the back. And imagine the nitrogen, I come and attach it here, okay? And then I just change, I put it at the back. This will still be one, two, three. It's going, if you count, let's do that. Let me write on the new diagram that I'm writing here. So we say the nitrogen, the N3 that is coming in is going to attach from the back. So we put it like this. This is from the back. So already that means that this D is going to be in front. Okay, like that. Then if you want to determine configuration, this is going to be 1. And in this case where it's going to be 2, let's say 2 is this one and then 3 is this one here. If you count from 1 to 2 to 3, this is also going, is giving us R, but because the fourth group is at the back, that is going to be S. But then if we are counting D, let's say as an atom that has got a higher molar mass, then that would have meant that this would have meant our first group is going to be this one, D is going to be the second, the third would take this one. This is still the R. But for this one here, still, this is going to be 1, this is going to be 2, and then this is going to be 3. Because we have solved configuration, even the configuration here will still change. So this is it. Make sure that there is a reversal in the configuration of the compound that you are writing. Yes, please. That's dimethyl sulfate. It's also a solution which we are using. So remember, reactions are supposed to happen in solution. Okay, so here is our nitrogen, and then our D is still there. Okay, so this is going to be the product. You can see the leaving group left, and then our compound came to attach from the back side. And then the one which was at the back now is in front here. Let's look at this one. Again, you need to identify the leaving group, and also you need to identify the nucleophile. So what is going to be the nucleophile here? Is going to be hydroxide, because the potassium is really not affecting the reaction. This compound that I'm drawing here, you really understand it when we talk about when we start alcohols in the next class. So it's a good leaving group. Tosylates are good leaving groups. So for this one, what is going to happen? You have got hydroxide, but then let's look at our compound that's supposed to attack this one here. You can see that this is a tertiary carbon. So a tertiary carbon will not go by SN2. Instead, it is going to take SN1. And look at the nucleophile. You also have a strong nucleophile, but then will not consider the nucleophilicity in getting to attack. You actually consider what you are attacking the substrate. It is more hindered. Okay. So because the substrate is more hindered, it's going to be, it will not go by SN2. So what will happen first is that this group is going to leave. And it leaves because it is a good leaving group. So what you remain with, so you have got this with a positive charge here because this group has left. You can just show it there. It is a byproduct. The oxygen is going to be with a minus there, then a sulfur like this, alternating bonds inside. Now what you formed here, now you can attack using your nucleophile. Every time you're talking about SN1 reaction, remember we said that SN1 reaction, the product is going to be a racemic mixture. You can either attack from the back or from the front relative to where the leaving group was. And so you're going to have two different products as a mixture of enantiomers. So what you are going to have here is the incoming group can actually just get to attach. If you want to show stereochemistry, you can have this guy being on a dash and then the coming in being on a wedge, or you can also swap them. Okay, so the methyl which is already here can be on a dash, the which can be on a wedge, or it can be the opposite. So in other words, one can be equatorial, one is axial, or it can be the opposite way. So that is how the configuration is going to be. But for this one, you can simply write lines. So you can see the OH can either be axial, and then the methyl is equatorial, or the other way around. So that is going to be the product here. Is that okay? Okay. And then the next one, number 4, you can see we have got our substrate, and then the nucleophile that we are using is in excess. And that should mean something. It means that it can react as many times as it can because it is in excess. So we have got a nitrogen here. How is this bond even? Okay, this is a triple bond because between two nitrogens you actually have a triple bond. This nitrogen is positively charged. Then we have got also an ethyl group. There's actually a carbon here and then another carbon, so that's an ethyl group. So we have got now our ammonia, which is acting as the nucleophile because ammonia has got a lone pair of electrons. So again, we need to identify the leaving group here. Okay. Of course, nitrogen is more electronegative than carbon. This positive charge that you can see is showing the formal charge of nitrogen. Otherwise, when you're comparing nitrogen and the carbon, nitrogen is partially negative, carbon is partially positive. So there's a difference between partial charges and formal charge. Formal charge is telling you about the number of electrons that is in the outermost shell of the nitrogen. That is why the positive charge, because nitrogen is initially supposed to be in group 5 and then it has got 4 electrons in the outermost shell. So 5 minus 4, that is a positive charge that you can see. But then in talking about electronegativity, nitrogen is negative in comparison to carbon. So when you are attacking, the nucleophile attacks what is positive, yes. Why? Because nucleophiles are negative. And the leaving group is going to be obviously this same big group here. That is the one which is going to be able to leave. Because it is more why is this carbon here not the one taking electrons? Because the electrons are going to be taken by the atom that is more electronegative, which has got capacity to pull electrons towards itself. So that is why that one is the one which is taking the electrons. So what you're going to end up with is going to be, now because this reaction is going to be going by, look at this. What kind of substrate do we have? What kind of substrate do we have? Is it primary, secondary, or tertiary? It is tertiary. So the reaction will actually not be even by SN2. It is going to be by SN1 because it is tertiary. So the nitrogen will first leave. So what we are going to have is this guy. At this point, look at what we remain with. Remain with this. There's going to be a positive charge here. Why? Because this guy has left. It's not even necessary to show configuration when one group has left because you only have three things attaching to this carbon. Configuration becomes important when you have got four things attached to that carbon, not less than four, not more than four. Okay. And then at this point, this is when now our nucleophile can come in. And it can tack from any direction because it is via SN1. It can come and attack here, or it can come and attack from the back. So I'm going to use one. So when it comes to attach from the, let's say it attacks from the back, so it's going to be there. We have got nitrogen, it's bonded to three hydrogens. Let me show, can I just write it on top? Because there's no space here. So if it attacks from the, let me say it attacks from the front, so we are going to see it like this. Okay, so I've got nitrogen. Remember, this nitrogen has got three hydrogens. Now when nitrogen is bond has four bonds, it's going to have a positive charge. The other group, which is this a few here, is going to be now from the back, like that. The other thing that would have happened would be the opposite. It would have attached from the back the same nitrogen with the three hydrogens, and it has a positive charge. And then the ethyl group would be in front, like that. But then I'm going just to take one because the same thing that we are doing for one is what we do also for to the other. Normally, you don't want to form products which are charged because they are unstable. And because our nucleophile is in excess, what will happen is that the nucleophile again come in. It will come and grab one of these hydrogens, breaking the bond. And so the product that we'll now have is a nitrogen bonded to two hydrogens. And this one is not charged. That is a stable product. It will be the same thing for the other enantiomer. So it is plus enantiomer. The other one where this group is at the back, this one is in front. So that is going to be it. And then for the next one, this one here. Again, you want to identify which one is going to be the nucleophile and which one is going to be the electrophile. So when you look at this compound here, already you can identify that this one has an halogen. Obviously, it should be the one which you are attacking. But then what is going to be attacking? You need to identify the nucleophile. Which one do you think is going to be the nucleophile? Obviously, if the electrophile is in this compound, the nucleophile should be in this one. But which atom exactly is going to be the nucleophile? So you look at the atoms which are present. You have got oxygen and nitrogen, but you have got two nitrogens. These are the only possible atoms that can attack, which can act as nucleophiles. Then when oxygen is in a bond here, in a double bond, nucleophilicity has been reduced because it is more stable. This nitrogen again is near oxygen, so also its nucleophilicity is reduced. This nitrogen is near carbons, so it has got more capacity of actually getting to go and attack. At the same time, it also has lone pairs, just like the other nitrogen. Even this oxygen has got lone pairs. But then this one is going to be a beta nucleophile. And so for this reaction, this is going to go by SN2 because this D could be a hydrogen and that is going to be a secondary substrate. Every time you're writing SN2 mechanism, there's always a carbocation intermediate that you need to include. So as this guy is going to attack, you'll not just end up with your product just like that. So here, remember this one is attacking this one here. How best do I even write it? Okay, let me write it like so. It is attacking. It is coming to attach on this carbon which is like this, which has got a D this side. So this is supposed to be here on the corner. Don't forget the alternating bonds. So there's always this intermediate where for SN2, one bond is breaking while the other bond is forming. For a detailed SN2 mechanism, you need to include the intermediate, this one. And then the next step will be now the full breaking of this bond. It will now fully break. This one which is coming is now going to fully form. So that is going to be our final product. This is now gone. Okay. And then we have formed a new bond. Remember, this guy is, there is a reversal in configuration. So this is attacking from the front because our leaving group was at the back. That is important. I would have written this group down. Is this okay? Okay. And then question 2, outline a detailed synthetic scheme on how you would carry out the following reaction. You just want a scheme, a plan of how you can carry out this reaction. We don't need a reaction mechanism. Now you can see that chlorine has been substituted by cyanide, but one interesting thing is that there is no reverse of configuration. What mechanism do you think happens without reverse of configuration? Okay, so SN1 does have reverse of configuration. There's another hand. Okay, so SN1 does have reversal of configuration, but the only thing is that you have got two products. You have got a product where, because this group has first to live by itself, all right, you are going to remain with a positive charge here. Now the cyanide has got a choice to either come to attack from the back or from the front. So you are going to have two products where cyanide is on a dash or on a wedge, but we are only picking the one which is on a wedge. But there is also some reverse of configuration. It's just that the product is a mixture of enantiomer. So in this reaction, because it's going to go by SN1, okay, you want to outline a detailed synthetic scheme. You know that the first thing that is going to happen is that you need to make sure that, look, when you're talking about SN1 reactions, which solution does it go well by? Is it in a protic solvent or aprotic solvent? Okay, a protic solvent. Why should we carry out our reaction in a protic solvent? All right, so that is the thing. You want to use a protic solvent because it's going to be able to stabilize our carbocation intermediate. So we can use a solvent made from the same thing that we use as our nucleophile there. And what will happen is that this same solvent will act also as a nucleophile. It's protic. This solvent can actually get to stabilize this thing because this solvent is actually polar, right? It is polar. It can get to stabilize this molecule. And then the nucleophile that we can use is going to be the same cyanide, but when you're talking about it as a nucleophile, you just attach group 1 elements in front like potassium, sodium to just stabilize the charge because cyanide is negatively charged. Okay, so we're going to have two steps. The first step, remember, is going to be this thing getting to live by its own. So in that first step, when this thing leaves, the leaving group leaves, you have this product with a positive charge here. But then that is going to be stabilized by our solvent. Okay, so the chlorine has left. And then in the second reaction, that's when we are going to have our nucleophile. And it can either attack from the back or from the front. That's how we are going to end up with our product, which is there. And preferentially, we have picked the one where the attack was from the same side of the leaving group. So we'll just put it there. So that is how the reaction is going to go. Consider a reaction shown below. Predict the major products of this reaction. You decide to quadruple the concentration of the nucleophile. By what factor does the rate of the reaction increase? Justify your answer. Now again, remember you need to identify the nucleophile and also the electrophile. That is the most important thing. Because if you'll not be able to identify that, you'll not know what is really going to happen. Alright, so here is our compound. And we have got our our nucleophile as the cyanide ion. Always look at the carbon atoms which are going to be positively charged. And those are the carbon atoms attached to electronegative atoms like oxygen. So this carbon here is going to be the electrophilic carbon because it has attached to oxygen. So this is partially positive. But then because this carbon atom that you can see here is tertiary, this reaction is going to go by SN1. So this group will first leave. When it leaves, you are going to end up with a carbocation intermediate. And so this guy here is going to be positively charged. That first step doesn't involve the nucleophile. And it is the rate limiting step. And then in the second step now, this is going to come in and attack. And the attack can either be from the back or from the front. And so our product is going to be a mixture of enantiomers. So the cyanide can either come and attack, it can come axial, or I could have put it here and then the methyl here. Or I can simply say, I can simply write this product here and put plus enantiomer because you're supposed to produce two enantiomers where the cyanide is either at the back or at the front. Now, if you increase, you quadruple the concentration of the nucleophile. This is SN1 reaction, and SN1 reactions don't depend on the concentration of the nucleophile. So that is not going to affect the rate. It doesn't matter how much you increase the concentration of the nucleophile. An attempt to prepare 2-methoxy 2-methylpropane by reacting 2-chloro-2-methylpropane with potassium methoxide was unsuccessful. Instead, 2-methylpropene is obtained. Briefly explain why butyl-methyl ether was not obtained. Give a mechanism. So this is a topic that will start tomorrow. But because it's a tutorial sheet, we have to answer it even if you've not really done. So look at what we are starting with. We are starting with 2-chloro-2-methylpropane. It's propane. So 1, 2, 3. It is 2-chloro. So there is a chlorine here. And then 2-methyl. So there is a methyl here. We can as well call this as isopropyl. Or what's another term? Chloroisopropyl. I've forgotten the other term. The What you do is you look at just if something is making like a Y. How many carbons are here? 1, 2, 3, 4. Oh, these are 4 carbons, so it is going to be a tet. If you see a compound that makes something like this is the one that you can see. That is tet. Iso, you have got 3 carbons. It makes like a Y. So tet butyl chloride. Now this is what we have, and we are told we want to prepare 2-methoxy 2-methylpropane by reacting this compound with potassium methoxide. From methoxide, that was coming from alcohol, and the alcohol is a methanol. We are putting potassium here. We're supposed to have a hydrogen to form methanol. Potassium doesn't affect anything, so this is a nucleophile. It's actually supposed to be like this, negatively charged. This is from the potassium methoxide. Now, the product that we are trying to get was supposed to be 2-methoxy 2-methylpropane. So 1, 2, 3. 2-methoxy, supposed to have like that. Okay. At carbon number 2 is supposed to have a methoxy and then 2-methylpropane. This is the methoxy you can see. So when you have got an ether, this is how you name it. We'll talk about ethers in the next class anyway. This is a product that we are trying to get. An attempt to make this was unsuccessful. Instead, what we ended up getting was 2-methylpropene. 1, 2, 3. It's a propane, remember? Okay. So you can number it as 1, 2, 3. When you number, you need always to make sure that you include the double bond in the numbering. So always start from where the double bond is. 1, 2, 3. You can see at position number 2 I've got a methyl, so this is 2-methylpropene. The question is, why did we get this instead of getting this? That is what the question is saying. Briefly explain why tet-butyl methyl was not obtained. Why didn't we obtain this tet-butyl methyl ether? This is the other name for this guy. You see when you talk about the nomenclature of the ethers. When you are naming ethers, basically just name what is attached to the oxygen. You have got a methyl, you have got a tet-butyl. So that's why you can see tet-butyl methyl and then just put ether at the end. Or another way you name ethers is name the groups according to alphabet. Okay, so you have got two things always attached to the oxygen. You have got this group here and this group down. The group on top is only having one carbon, so that is a methyl. The group down is a propane. Look at this. This is a propane, but it has got a methyl. So that is methylpropane. You're actually even stating the position of the methyl. So that is 2 methyl and then propane. Because if you number this as 1, 2, 3, you can see the methyl is at position number 2 of the propane. So you always want to number first what comes early in the alphabet. You have got a P here, that's for the propane, and then you just have the meth. So M comes first. And the one you are naming first, you always put ox at the end. So here names like ethox ether, methox ether, methox ethoxide. So names like that. Anyway, we're not talking about nomenclature of ethers. So in the mechanism that you can see here, we did talk about SN reactions and E reactions. By elimination, you are going to form an alkene. And then by substitution, you are going to form the ether. So initially what was supposed to happen is that this guy was supposed to go and attack and then we get to form our product. Okay. Like we're supposed to go and attack. This guy was supposed to go and attack here, displacing the chlorine. And then we form our product there. But then that didn't happen. And the question is, why didn't it happen? Look at the substrate. The substrate is a tertiary substrate. It is hindered. Because it is hindered, it is very hard to go by SN reaction mechanism. So instead, what is going to happen? It can go by E mechanism. And by E mechanism, you always look at the group, okay? That the carbon attached to the carbon having the leaving group. This is the carbon having the leaving group. So any other carbon attached to it just grab a hydrogen from it. That bond breaks, forming a double bond, and that causes this group to leave. That's how you end up with something like this. If I write it just the way I've written it, there's a double bond that will be able to form here. The chlorine has left. This compound is this one that you can see. So it is easy to grab the hydrogen at the end here than us going to attack. But then, because this thing is tertiary, the mechanism is not even likely going to happen by the 2. It can happen by the 1. That is E1 or E or SN1. Let's say if the mechanism is supposed to happen by the 1. We've already seen what is going to happen. Now I'm just trying to show you what would have happened if it was supposed to happen by the 1. So if it was happening by the 1 mechanism, the first thing is that the leaving group is going to leave. We end up forming our carbocation intermediate. And can I write it like this? Because we're going to have these 3 groups as the only things which are remaining. So this is a positive charge here. Now look at our attacking group. Our attacking group is a methoxide, right? That is OCH3. You can write it like this, or you can write it like this. It's all the same thing with a negative charge on top. Now this guy is a strong nucleophile. And we know that for SN1 reactions, we don't care about the nucleophile. Okay, we don't care about the nucleophile. So this really is not going to go about that. We don't, because SN1 reactions prefer going by a weak nucleophile, but this one is a strong nucleophile. So the reaction still prefers getting to grab a hydrogen here and then this bond getting to break. Okay, so that is why. So briefly explain why tert-butymethyl ether was not obtained. Because the reaction is going to undergo elimination instead of substitution. When you get to use this nucleophile that you have, the potassium methoxide. Give a mechanism to account for the 2-methylpropane product. We've already talked about how the mechanism is going to happen, isn't it? We've already written the mechanism. Yes, please. This compound is tertiary. For tertiary compounds, E1 or SN1 can happen. So that would depend with the solution that you have. If in solution we have got a protic solvent, this thing chlorine can actually go and then will stabilize our ion that we form. So that is by the 1 mechanism. But then for this one, we haven't even been told the solvent that is there. So the reaction can even go by E2 because we don't know the solvent. If it is a protic solvent, we know that the reaction is going to go by 1 because it's going to stabilize our ion. For this one, we can as well take it by the 1 by the E2 mechanism, where we are going to grab a hydrogen that is 1 carbon away from the carbon carrying the leaving group, and then this bond will break, and then this bond will also break, and then we end up forming our product. Is that okay? Okay, so that is going to be it. The last question. Compound 1 containing a 14 carbon atom indicated by star forms compound 2 as a major product upon reaction with potassium methoxide. Provide an explanation for this result. So here is our Br. So this is an epoxide. got a star there, and then we are reacting with potassium ethoxide. Ethoxide, we have got oxygen bonded to an Fu. This is negatively charged. So normally what happens is that this guy is going to attack a carbon that is attached to the oxygen. Okay. And actually what was supposed to happen is that we want the leaving group to go. So this could have attacked here and then cause this group to leave. Okay, like that. And then the product that would have formed would have been this. Remember there is a star here. So we have this thing has gone, so oxygen is going to now come and attack here. And remember the oxygen is got as also a methyl. But then this product is not this product. You can see the star is here, but here the star is here. So this reaction doesn't happen like this. Why? This ethoxide is going to attack the carbon that is having the oxygen instead of going to attack the carbon having the leaving group to displace the leaving group. Okay. And you don't go and attack here because this guy is more hindered. So when these reactions with epoxides are happening, you attack the carbon that is attached to the oxygen, but then it is less hindered. So that's why we are going to go and attack this carbon here. Okay. And when we attack, every time you attack the carbon, we call it the opening of the ring. The bond here is going to break. We open the ring. And see what we're going to have. We still have Br. We have like that. So let me write the oxygen down here. And this oxygen is going to be negatively charged because it has carried those two electrons. It already has also two other electrons. You know how water is bonded to two hydrogen. It has got two lone pairs. So same with this oxygen, it's bonded to two carbon, so it's going to have two lone pairs. So it's negatively charged. But remember there is this bond here. Okay, this same carbon having that oxygen is having a bond. And remember this carbon here is the one with a star. And we have attached oxygen to that carbon. So we have attached oxygen. This oxygen has got a methyl like that. This is the product that we have. Now, this compound is not stable. Remember what we said, that you don't want to form things which are charged. So the oxygen is a strong nucleophile here. Because it's a strong nucleophile, it is going to go by SN2, attacking itself, attacking this carbon that contains the bromine, and the bromine acts as a leaving group. And so what are we going to form? I want to make it as simple as possible. I'm going to write this oxygen, and with this bond that you can see, this bond, I'm going to write that bond. Remember, it is forming another bond this side, okay, with this carbon. But remember, this carbon and this carbon, they are attached. So these two carbons are attached. This bromine has left here, so there's nothing. This carbon here is attached to another carbon, and this is a carbon here. But remember, this carbon has a star. And this carbon is attached to oxygen. And then this oxygen is attached to methyls. So this is going to be our product. And this is a product that you can see here. Now I've just written it in this direction. Can flip it in the other direction like that. It's the same product. So this accounts for the product that has been produced here.